So as we move through this section, for convenience, I want us to denote compound statements with capital letters, right? Remember, simple statements, we use lowercase letters, but for compound statements, we're going to use capital letters. If P or Q is logically equivalent, we write P implies Q whenever the biconditional between P and Q is a tautology, right? Meaning they have the same truth values. So let's go over a list of some of the equivalency laws. There are some we're going to use more than others, but I want to take a look over them. You can find a list of all these equivalency laws on page 512, but I have included them in this PowerPoint for convenience. So there's some that we've seen before, like double negation. Two negatives make a positive. We have commutative laws. P or Q is the same as Q or P. P and Q is the same as Q and P. Those are things to keep in mind. This is supposed to have a double biconditional statement between it. I don't know why PowerPoint does this to me. Okay, we also have associative laws, right? Remember, multiplication is associative, addition is associative. So that just means we can move our parentheses grouping as long as we have the same symbol. The same thing for we can distribute as well. We also have some identity laws. Given a P and a contradiction, your outcome's P. Given P and a tautology, your outcome is a tautology. Given P and C, you'd get a contradiction. P and T would be logically equivalent to P. P and P or not P is logically equivalent to a contradiction, and so is P and not P. Contrapositive, that's something we're going to prove in just a second. We also have implication, so ways we can get rid of this little arrow symbol. That's going to be a big thing we're going to focus on in this section. And equivalence. So remember, the biconditional is equivalent to P implies Q and Q implies P. There's also one law that's really just kind of ridiculous. It's called Reductio Ad absurdum. My pronunciation is terrible. That was supposed to be Latin. And what it means is reduction to obscurity or argument to obscurity. This argument is used to prove a statement is true by having a false or absurd result denied from its denial. So P implies Q is logically equivalent to P or not Q implies C. So an example of an obnoxious argument would be rocks have weight, otherwise we'd see them floating in the air. That's a ridiculous argument. So let's go ahead and look at double negation real quick so we can talk about the simplest example of logical equivalence and what that looks like. So double negation is logically equivalent to P. It is the case that I'm not going to a party. It is the same as... So if I say I'm going to a party, that's the same as it's not the case that I'm not going to the party. That means I'm going to go to the party. So here we make our truth value table. We only have one variable, so I didn't need all this extra space down here. That was silly of me. So not P would be false, true, and then not P would be true, false. Because both of these columns have the same truth values, they are logically equivalent, because if we put a biconditional between them, we'd have a tautology, which means they would be true. True implies true is true, false implies false. Both ways is false. Okay, so there's the table all worked out. Kind of reductive, because I did each variable twice, which wasn't necessary. Let's take a look at proving the logical equivalence of the contrapositive. So I'm going to go ahead and make my truth table, which we're all very good at by now, right? Just filling in our trues and our falses. Not P would be false, false, true, true. Not Q would be false, true, false, true. P implies Q is only true if my conclusion is only false if true implies false. So here I have true implies true, which is true. True implies false, which is false. False implies true. Where did I go? Okay. False implies true, which is true. False implies false, which is also true. Now I've got not P implies not Q. So false implies false. That is true. True implies false, that's false. False implies true, that's true. And true implies true, that's true. Because both of these columns are the same, they are logically equivalent. I did include the solution in the PowerPoint so you can check your answer. What's the contrapositive represented in English? A big part of section 11.5, which we're coming up to, is translating sentences and statements into logical notation, right? So, for example, if there is cake, then there is ice cream. The contrapositive of that would be if there's not ice cream, then there is not cake.